Hi, this is Dr. Golding, and today we're going to talk about 7.1 Roman numeral 3. What's going on in this set of exercises is that you're constructing proofs using the four rules that we learned last time in order to show that from certain premises you can derive a certain conclusion. So the entire set of exercises is basically what's called doing proofs, in this case using only four rules, because in Unit 7 or Chapter 7, each section introduces new rules, and the rules, in a way, they kind of build upon one another. You learn one set of rules, then you learn another set of rules, then another set of rules. You learn a lot of rules in Chapter 7 in order to do proofs. So we'll take it a step at a time, but right now in 7.1 Roman numeral 3, you're asked to do proofs using the rules that we learned. Now, first of all, you've only learned four rules so far, so I'm gonna put those rules on the board just to remind ourselves of what they are. We have P horseshoe Q, therefore Q. That is the rule known as modus ponens, or MP. We have modus tollens, which is P horseshoe Q, not Q, therefore not P. Right? You have the horseshoe, then you have the negation of the consequent, therefore the negation of the antecedent. This is known as MT, or modus tollens. And let's see, we had a disjunctive syllogism, that's DS. Disjunctive syllogism, now I've told you that there's two forms of DS. You have a disjunction and the negation of the first half, or the left half. You're allowed to infer the negation of the right hand. You also have P wedge Q, not Q, therefore P. This is also, see, I made a mistake here. This should be Q. You have the disjunction, you negate the first half, you're allowed to infer the right hand side. Or if you have a disjunction and the negation of the right hand side, you can infer the left hand side. Both of these are called disjunctive syllogism. Sorry if I'm going off your screen here. This is disjunctive syllogism. And what was the other rule we had? The rule of hypothetical syllogism. Okay, hypothetical syllogism is you have, maybe I better write it over here, P horseshoe Q, Q horseshoe R, therefore P horseshoe R, that's hypothetical syllogism, HS. Okay, so now let's see what a proof would look like using the four rules. And we'll talk a little bit about the strategy behind being able to do a proof. One of the things about doing proofs is they can be fun, they can be challenging. Also, one reason why they're kind of interesting is because they're, in many cases, as we'll see, there's more than one way of doing a proof. Now with these exercises here in 7.1 Roman numeral 3, basically, there's only one correct way of doing it because they're basically pretty simple, but as we get further on in Chapter 7, we'll see that there could be different legitimate ways of doing a proof. So we're going to talk about some strategies of how to do a proof. We'll also talk about the fact that, well, I'll just say this up front, is that if you're doing a proof and you have, let's say you have a step in your proof that turns out to be extraneous or extra, it doesn't hurt your proof. It doesn't damage the proof. It just makes the proof a little longer than it had to be. Okay, so as is the case with any argument, if you have a series of premises and you can get to the conclusion logically, it could be the case that some of the premises aren't necessary for reaching that conclusion, but it's still a valid argument. Okay, well, in the examples in the book, they will never give you premises that are irrelevant or that don't need to be used in the proof. That's just the way these exercises are constructed. They give you a set of premises. You're going to have to use all of the premises to get to the conclusion. My point was, though, that if you have an extraneous step, that does not make your proof wrong or bad. As long as every step in the proof is justified by a rule, and as long as the last step is the desired conclusion, then you have a good proof for that conclusion. Okay, so let's take a look. Really what your homework is to do 7.1 Roman numeral 3. There's a lot there. There's, at least in my book, I see that there's 25 examples. I would say you should do, ideally you should try to do all of them. At least do, at least try to do, probably at least try to do 1 through 20. So this is your homework, is 1 through 20. Now I'm going to do a few of them today on the board, so you really don't have to do those for homework. So let's just get started. I'm going to start with number 1. You're given 2 premises, and you're supposed to derive the following conclusion. We have step. Now I am going to have to erase. I think you have these rules in your book, so I'm going to erase them now. You're supposed to know them by heart. What the rules are and what the names for the rules are. Okay, so let's see. Number 1 is we have 2 premises. We have not C, horseshoe, A, horseshoe, C. And we have not C. And we're trying to prove, it says not A, right? That's listed over here. Is it A or not A? It is not A. Okay, tilde A. So this is how you start the proof. You simply write down the first 2 steps. Those are premises. And over here, you write, this is the conclusion that you're shooting for. Now, what I would say is that, I'm going to move this over just a little bit. Okay, that's what you're trying to prove is not A. That little line represents, that's what your conclusion is supposed to be. Now, something I like to do that's a little bit different from the way you'll see, I think, the book does proofs is, over here should be listed the justification. In other words, this is justified because it's a premise. So I'm going to put PR. That's a little, PR represents the word premise. The justification for number 1 is that, well, it was given to us as a premise. So I'm going to say premise. And this is also a premise, right? Now this is not a premise. This is what I'm supposed to be concluding my proof with. So right away, here's the strategy for doing proofs is you're optimistic that you're going to be able to get to your conclusion. The conclusion is not A. So I'm going to write down not A over here. I don't know what number it's going to be. Each step should have a number. And each step should have a justification. Aside from the premises, each step is going to be justified by some rule that you use. Now, right now we only have 4 rules, so it's going to be one of those 4 rules. But I'm trying to get to not A out of these 2 premises. So, what should I do here? Well, here's something that I see I can do. I can use the rule of modus ponens right away, even without thinking about how am I going to get to not A. This is part of the strategy, is just apply rules. If you see that there's a rule that you can use it, and hopefully eventually you'll see how you're able to get to the desired conclusion. But I see right away that I have a horseshoe. and I have the antecedent of the horseshoe. And there's that rule, remember, modus ponens allows you to get from a horseshoe with the antecedent, you're allowed to derive the consequent. So I'm going to go A horseshoe C by modus ponens MP on 1 and 2. That's listing the justification. The rule of modus ponens applied to number 1 and number 2 gets me the consequent, which is A horseshoe C, and I don't need to keep the parentheses because A horseshoe C is obvious as to what it is. The major operator is the horseshoe. There's no ambiguity, so I can erase the parentheses. Now, I'm beginning to see, well, here's A. A is sitting inside here. Is there some way that I can get not A out of A horseshoe C? Well, not by itself, of course. I can't just derive A from A horseshoe C alone, but I can do modus tollens. I see over here I have not C. So I say modus tollens on 2 and 3. Sorry, not 2 and 3. Yes, 2 and 3, indeed. Modus tollens on 2 and 3 gives me not A. So actually I got to not A in only 4 steps. So I can erase it from here and just move it up to here. This is a proof. I started with these 2 premises and I got to not A, which was the desired conclusion. So this is a valid proof using the rules showing that from these 2 premises I can indeed get to not A. That's a relatively very simple example of a proof. So what you should do is work on your own to try to get into the hang of doing these proofs using these 4 rules. As chapter 7 goes on, you start learning more rules and the proofs start getting longer and more complex and sometimes harder to do. But that's basically what we're going to be doing pretty much for the rest of this semester, is learning how to do proofs in propositional logic. And that's going to be a good part of what is on your test at the end of the semester, is proofs. We'll talk more about what's going to be on the final, but proofs is certainly going to be a good part of it. Now then, let's take another example of a proof. I'm going to pick, I'm just going to try to do number 8. Okay, I'm going to do number 8. Why don't you try doing that? You can maybe turn the video off, try doing number 8 on your own, see how far you get with it, and then turn the video back on and you can watch me go through it. But this is going to be number 8. We have A horseshoe, E horseshoe not F. We have H wedge, not F horseshoe M. We have A, and we have not H. And we are trying to get to E horseshoe M. We're trying to get to E horseshoe M. So, like I said before, actually this would be a little bit misplaced here. Okay, again, I'm going to write the justification going down the side next to each step. Each of these are premises, so I'm going to say PR, 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 and PR. These are the 4 premises, that's their justification. Okay, so again, strategy here is look at what I'm trying to prove, But also, just if you see a rule, use it. Whenever you see you can do something with the premises, get yourself started. I see something that I can do. Does anybody see a modus ponens here? Yes, I see a modus ponens because I have a horseshoe. You have to just sort of look for modus ponenses, look for modus tolenses, look for disjunctive syllogism. There's also a disjunctive syllogism we could do here. Maybe you see it. We have a wedge in number 2 and we have not H. So we could use disjunctive syllogism on 2 and 4. We could also do modus ponens on 3 and 1. In fact, we're going to have to do both. Now, here's a question. Does it matter what order you do this in? No, it does not. It doesn't matter whether you do the modus ponens first or you do the disjunctive syllogism first. So I'm going to say like this. I feel like doing disjunctive syllogism first. So I'm going to do 2 and 4 disjunctive syllogism. I get not F horseshoe M by a DS, disjunctive syllogism on 2 and 4. Okay, and I'm going to do a modus ponens on 1 and 3. So I'm up to step 6. Modus ponens on 1 and 3. Again, this is a horseshoe. I hope that's clear. All right, so we get E horseshoe not F. Modus ponens on 1 and 3. And now, let's see, make my E a better E. Okay, now I've used my premises. I got to these two. Is there some way I can get to E horseshoe M out of these two, or do I need something else up here? Now, the fact of the matter is that I'm looking at this is a horseshoe. We know that there's one of the rules that involves horseshoes in a big way, right? Remember, it's hypothetical syllogism. That's the rule that says if I have P horseshoe Q, Q horseshoe R, I can then go to P horseshoe R. And that's exactly what I have over here. I have E horseshoe not F horseshoe M. So I would call not F the middle term. It's basically could be the thing that replaces or stands in for Q. E would stand in for P. M would stand in for R. So I can say, here's step 7, by doing a hypothetical syllogism on 5 and 6, this is an S. Hypothetical syllogism on 5 and 6. At step 7, I get E horseshoe M. So that's the conclusion. That's the desired result. I've shown that based on these premises, using each of these rules on each of these steps, I can get to the conclusion. Now again, if I had some kind of an extra step or I did something extra, extraneous, that wouldn't make the proof wrong. It would just make the proof longer than it had to be. So that is this again was number 8 in Roman numeral 3. So, let me try another one from this set. I'm thinking of I'm going to try number 12. Okay, let's try number 12. You can try it on your own, turn the video off, and see if you can do number 12. Number 12 goes like this. Not M wedge, B wedge, not T. B horseshoe W, not M, not W, therefore not T. Now, later on, we're going to learn that there's a rule, which we're going to learn about later on. It's not in 7.1, but there's a rule called double negation. Double negation is a rule that allows you to take off two tildes from a formula that has two tildes, because obviously not m is the same thing as m, right? It's logically equivalent to m. If you did a truth table for not m, and for m, you'd see that they come out exactly alike. Of course, they're going to come out exactly alike, right? If m is false, not m is going to be false. And if m is true, not m is also going to be true. But we don't have the rule of double negation yet. Okay, so this is a very important thing, that in this section, you're given 4 rules. You're not supposed to do any other tricks. You're not supposed to do any other logical moves other than what those 4 rules will allow you to do. So I can't just say m here because I don't have the rule of double negation yet. Later on, you're going to have it so then you can use it. But as of now, all you have are those 4 rules that we said before. Modus ponens, modus tollens, disjunctive syllogism, and hypothetical syllogism. Okay, I look at these 4 premises. I'm trying to get to not t. What should I do? What can I do? Well, I don't see any modus ponens because I have a horseshoe here. Do I have b by itself? No. However, I do have not w, so I can do a modus tollens on 2 and 4. Let me go ahead and do that. I'm going to do not b by a modus tollens on 2 and 4. Okay, now what else can I do? I see over here, sometimes it's helpful to put a little check mark over here because I used b horseshoe w. I broke it down, so to speak. I also used number 4, right? Now, often what happens with these proofs is that once you use a premise, you're probably not going to have to use it again because you broke it down, you did something with it to make progress. So you're probably not going to have to look at 2 and 4 again, probably. But you didn't use 1 and 3 yet. Is there something you can do with 1 and 3? Do you see it? Yes, indeed, there is something. This is a disjunction. What rule is there for disjunction? What rule allows you to do something or break a disjunction down? It's disjunctive syllogism. You actually have not m. That's the negation of the left-hand side. So you can do disjunctive syllogism on 1 and 3, because remember, disjunctive syllogism is P wedge Q, not P, therefore Q. So you have not m. That's like having the negation of P. So with 1 and 3, you'll get the right-hand side. The whole right-hand side is B wedge not T. This is disjunctive syllogism on what steps? 1 and 3. So now I have B wedge not T. I'm getting closer and closer to what I want, which is not T. Is there some way I can get not T out of here? Well, wouldn't it be good if I could have disjunctive syllogism on this? If I could do not B, well, I have not B. Ha! So there you go. I have not B. I see that together with step 6, I can do a disjunctive syllogism. I can get not T. Sorry, that's a tilde T. And that is disjunctive syllogism, ds on 5 and 6. And that is the conclusion of the proof. I reached my desired conclusion. Each step was justified. From these premises, I show that you can get to not T. Now, I just want to point out that the proof method, in a way, is a lot nicer and more pleasant to use. It's more interesting, but it's also more pleasant to use in the sense that if you were to do a truth table, remember the truth table method, don't forget about that. The truth table method for doing proofs, you have MBW, you you have four components in this argument here, right? You have four simple components. If I asked you what are the simple components of the argument here, you would have to say B, M, W, and T. So a truth table with four simple components is going to be 16 lines long. And on each line, you're going to have all those combinations of T's and F's, and you're going to have to be plugging through T's and F's for 16 lines and determine whether there's a counterexample. Is there a row where they all come out, the premises all come out true and the conclusion comes out false? Look what we have here. This is 7 lines. Elegance, simplicity, it's relatively short. We know that this is a valid proof because each step is justified by a valid inference rule. And the rules we know are valid because we can test them with the truth table method. So that's the elegance of the proof method compared to the truth table method. Okay, again, your homework is to do 7.1 Roman numeral 3. I'm going now to move on to 7.2 a little bit and talk about what's in 7.2. In 7.2, you learn some new rules. So what are the rules in 7.2? The rules in 7.2 are, it says rules of implication, Roman numeral 2, meaning you're learning more rules of implication. Later on, we're going to see there's a different kind of rule called a replacement rule. These are rules of implication. Okay, now the rules of implication here, perhaps, well, I'll write them on the board even though they're in the book, but let's start off with conjunction. That is a very easy rule. If you have P and you have Q separately, you can, this is called the rule of conjunction. Usually it's abbreviated as CONJ. Okay, so the rule of conjunction says that if I have P and then I have Q, let's say on two different lines in my proof, I can then conjoin them and say P dot Q, right? Definitely, this is a valid argument form. If you did a truth table for it, it's going to come out valid. Intuitively, you can see that, well, if P is true and Q is true, then P and Q have to be true. So that's a very simple rule, the rule of conjunction. Similarly, another very simple rule is what's known as the rule of simplification. Okay, now simplification, in my opinion, really has two forms. Simplification has two forms. This is one form of it. You have a conjunction and you break it down and say, well, if P and Q are true, then obviously P is true. I would say this is also simplification. If I have P and Q, I can go to Q. Both of these are called simp, abbreviated for simplification. To simplify a conjunction is simply to break it down into break it in half, so to speak. If I know that P and Q are true, then obviously P is true. If I know that P and Q are true, then obviously Q is true. So both of these are examples or good uses of simp or simplification. Now this would be bad, right? If I said P wedge Q, therefore P, that would be wrong because P wedge Q says either P or Q is true. It doesn't say which one of them is true. It's just saying one of them is true, but it doesn't tell you which one is true. So from P wedge Q, you cannot go to P and you can't go to Q, right? This would be a bad use of simplification. You cannot simplify a conjunction. Sorry, you cannot simplify a disjunction. That's what I meant to say. You can simplify a conjunction, but a disjunction, you can't do simplification on. That would be wrong. Okay, now those are so far the two new rules in 7.2. Now, here's a little bit of a complicated rule, constructive dilemma. And actually, this was one of the argument forms that we talked about at the end of 6.6. So what is constructive dilemma? Write it on the board. Basically, you have a conjunction of two horseshoes, P dot Q and R horseshoe, sorry, P horseshoe Q and R horseshoe S. And then you have a disjunction of the two antecedents, P wedge R, and the conclusion is, or the inference drawn is Q wedge S. Right, we talked about this in 6.6. You have a conjunction of two horseshoes, you have a disjunction, P wedge R, of the two antecedents. That tells you that Q wedge S is true, okay, because if both of these are true, that means that, well, this is saying, well, if P is true, then Q is going to be true. On the other hand, if R is true, then S is going to be true. So either Q or S has to be true. Again, you can do a truth table for this, but this is a small p. Okay, what is this called? Constructive dilemma, abbreviated by CD, constructive dilemma. Finally, the fourth rule is something called addition. Now, this is really a little bit of a weird rule. It's not a rule that you would use intuitively, but what is the rule of addition? It says that if you have P, you can add on P wedge Q. I think that the name addition is a little bit not the greatest name for this rule. Okay, addition. You're not adding anything. You're adding something in the sense that you're tacking on a string of formulas here. You're adding wedge Q, but the idea behind addition is that if I know that P is true, then that means that P or anything in the world is true, right? If I know that today is Thursday, that means it's going to have to be true that today is Thursday or the moon is made of green cheese. Because again, a conjunction is true so long as any one half of it is true. So if I know that P is true, or if I'm given P, that means that P wedge anything, whether Q is true or false, right? P wedge Q is going to be true given that P is true. So addition is a rule that allows me to wedge on any formula I want to some formula that has been given to me. It's not something that you would use in normal everyday English. However, the rule of addition turns out to be a handy rule when doing proofs. It's kind of like a logician's rule. It's not a rule you would normally use in ordinary English, but like these are. These, I think, simplification and conjunction are things that we do in our mind all the time. Addition is a little bit strange, but it is a valid inference. Any substitution instance of this form is going to be a valid move in logic. And so therefore, it is a rule that is used in this system. Now, I do want to say something about this. The rules here in chapter 7 is that there are many, many different books, systems of logic. If you were using a different book in logic, you might get a different set of rules. Because as I've mentioned before, and as you probably remember or you know, there are really an infinite number of valid argument forms. Okay, there's an infinite number of valid argument forms. So in any system of proofs where you have a set of rules, exactly what the rules are could be a little different from one system to another, or from one logic book to another logic book. The rules might be different. Some of the rules are going to be the same. I mean, I don't know of any system where they don't use something like simplification. But in any system of logic, there's going to be certain rules that are shared, and then there's going to be other rules which some systems have and other systems use different rules. Okay, we'll talk more about that point later on, but it's just something you should be aware of, that not every system in logic, not every logic book, not every logic teacher will use the same set of rules for doing proofs. But this is our book, and I'm the teacher, so these are the rules that you're supposed to know to get through this class. Okay. The next step here, now I do want to say about addition, I would like to say that there's two forms of addition. Maybe you can guess what I'm going to say. Here you have P and you inferred P wedge Q. Well, you can also go from P to Q wedge P. Okay, I can wedge on something on the right-hand side. I can also wedge on something different on the left-hand side. Okay, so I'm going from P to Q wedge P. Or this version. So there's two versions of addition, just like there's two versions of simplification. But why aren't there two versions of conjunction? Well, really there are two versions of conjunction because we could have put it this way, right? Well, what I was going to say was you can go P dot Q, you can also do Q dot P. Which one do you put first? Okay, well, either one of these would be right. And it also doesn't matter what the order of these are. Okay? Anyway, that's the 4 new inference rules that you learn in 7.2. And then the exercises are going to be similar to what you had before. You're going to have to learn how to recognize correct, or you're going to learn how to use the rules correctly, and then you're going to learn how to do proofs using not only the 4 rules we learned already, but also incorporating these rules. Now, I want to explain something is that as the chapter goes on, you're allowed to use all of the rules that you've been learning till then. So like, for example, when you get to your test, if we ever get there in this class, and I ask you to do proofs, I'm going to say use any rules you can, any and all of the rules to do the proof. So I'm not going to say, oh, for this proof, you're only allowed to use such and such rules. Okay? That's not going to happen. What's going to happen is you'll have proofs, and you'll be able to use, and indeed you will have to use all of the rules at your disposal to get through the proofs. Now, we are going to see that as we get to the end of Unit 7, there's some very high-powered rules that we're going to learn that will make some of these rules, well, actually not these rules, but some of the rules that you'll learn throughout Chapter 7 are going to become somewhat obsolete and unnecessary given the later rules that you learn. Okay, but for now, we have 8 rules. Modus ponens, modus tollens, disjunctive syllogism, hypothetical syllogism, simplification, conjunction, constructive dilemma, and the rule of addition. Those are the 4 new rules. So what I've asked you to do for homework really is already, I asked you to do 7.1 Roman numeral 3, but I would also like to ask you to start taking a look at 7.2, at least try to do Roman numeral 1. Okay, so let's do a couple of those together, and that's going to be it for this session. And we'll leave Roman numeral 2 and Roman numeral 3, I'm looking at the book here, for another time. Although if you want to read ahead and get ahead and do those 2, that might not be such a bad idea. But okay, let's spend a little time doing 7.2 Roman numeral 1. Why don't you try to do number 1 right now? Turn the video off, try to do Roman number 1, and see how you can do it, or see if you can do it. I don't think it's that hard. I'm looking at it right now. We see here several steps. S wedge H. We've got B dot E. We've got R horseshoe G. And we're given, here's step 4, what can I get, what formula can I get using simplification on what step? So this is a really pretty easy one, I think. Maybe I'm a little biased, but the rule of simplification is what? It says that when you have a conjunction, right, you're allowed to break it down into one of its sides. Okay? So there's only one conjunction here. It's sitting right here in number 2. So I would say you can get B by simplification on step 2. I would also say you could get E by simplification on step 2. Because you have a conjunction, you can break it down into either one of its parts. So the answer is simplification on 2 gets me B or E, whichever one would be a correct answer. Okay, let's see, these I think are relatively easy. How about, I'm looking at the book here, let's try number 2. Try to do number 2, turn the video off, pause the video, see if you can do number 2, and then I'll show you on the board number 2. Okay, so here's number 2. We have N horseshoe T dot F horseshoe Q. We have N horseshoe R wedged F horseshoe M. And we have N wedged F. And the question is, what can I get using CD on one of these steps, or in the case of CD, you need 2 steps. So CD is constructive dilemma. If I don't remember it by heart, I have to go back and look at the form until I begin to memorize the form for the form of constructive dilemma. Basically, constructive dilemma is you have a conjunction of 2 horseshoes, and then you have a disjunction of the 2 antecedents in those horseshoes, right? So you have a conjunction of horseshoes. Now, number 2 is a disjunction of 2 horseshoes, so it's not going to work with number 2. What is number 2 doing here? It's just there to distract you, to make the problem a little bit more challenging, right? You can't use number 2 for constructive dilemma. You can use number 1, because number 1 is a conjunction of 2 horseshoes, and number 3 is a disjunction of the 2 antecedents, right? We have N over here, and we have F over here. So the rule of constructive dilemma allows me to infer a disjunction of the 2 consequents, T wedge Q, by constructive dilemma on 1 and 3. So that is the answer to number 2. So it's almost 45 minutes of time. I'm going to stop here for today. Sort of in summary, what the homework is to do Roman numeral 3 from 7.1 and Roman numeral 1 from 7.2. All right, 7.1 Roman numeral 3, which I did a few of already, and from 7.2 do Roman numeral 1, and that way we'll be making progress on learning how to do proofs in propositional logic. If you're having any trouble, if you have any questions, if you have any issues, please email, call, write me a letter. Maybe that's not such a good idea, but please do be in touch. Let me know how it's going. Let me know how you're doing with these exercises. Stay healthy and be well. Again, you can, it would be a very good idea to, if you're not sure, especially if you're not sure if you're doing any of these right, to take a picture of your work, take a photo, a few photos, and then email them to me, and I'll be happy to look them over. Otherwise, have a good weekend, and I'll talk to you next week. Bye now.